Remember, the stability analysis that we performed was for a linearized system and therefore applies only to small displacements. And all of the results that we presented since then have also been based largely on linearizations. And so, as we've seen, even though we can recreate them in the full nonlinear equations, we really have to be careful about only thinking about small displacements from the linearized system. However, it turns out that large orbits around the two stable Lagrange points, those L4 and L5 points, are possible, and they're actually quite robust. And we can find two general classes of orbits, one called horseshoes, which are global about both L4 and L5 jointly, and tadpoles, which are local to either L4 or L5. So we're going to analyze these, but first, let's just demonstrate that these are feasible and achievable in the nonlinear system. We will use another MATLAB function that's very similar to the one that we used for generating the animations associated with our Poincare maps. So the way that this code works is we are going to be specifying a mu value, and here we'll initially use a 0.001 value and then a more specific value to illustrate a particular case. And then we also dial in an offset in our initial conditions that is added to the location of the L4 point. You'll recall that it's located at 0.5 minus mu in x and square root 3/2 in y, and we will be adding some offset to it. So in this first case, we're going to generate what's known as a large tadpole around L4, and we're going to offset from L4 by 0.008 distance units in both x and y, and we're going to leave the initial x and y velocities both at 0. So we run this. Once again, on the left-hand side, we're seeing the rotating frame behavior, and on the right-hand side, we're seeing the inertial frame behavior. And so you can see that what happened was our test particle first approached the moon in its orbit, and now is going further and further away from the moon in these closed structures in the rotating frame, and now it's coming back. So if you squint at the right-hand side rendering, you'll see that the distance between the moon and our test particle gets smaller and smaller as it returns to the vicinity of L4. And it's traced out this path that might potentially, if you squint at it, look something like a tadpole, and hence the name. Let's see what happens when we create a much larger offset. So here we're going far away. And again, these are very specific numbers found by looking at the recurrence map of this system for a particular mu value. And this is going to approximate what is known as a horseshoe, which is the global structure. So here we started all the way out at the L3 point, and now we are kind of spiraling inwards towards the moon. And again, on the right-hand side, you can see our particle approaching the moon, and now we're going back. And we actually do not stop at our initial point, but we go all the way on the other side towards L5. We're actually going to pass L5 and approach the moon again from the other side of its orbit, and then turn around and head back all the way to where we started. And this will repeat over and over again. And this is known as an approximate horseshoe because even though it has that global behavior capturing both the L4 and L5 points, it still has these little ringlets in the rotating frame. Finally, we can find a very specific set of initial conditions that give us a true horseshoe. And in this case, we are looking for the same global structure covering both L4 and L5, but with completely smooth contour lines in the rotating frame. And there we go. So our test particle goes directly towards the moon. It will perform a very close approach, turn around, and then follow the contour all the way back towards L5. And at the end of the day, we have a completely closed horseshoe shape. Let's take a closer look at the circular restricted three-body problem motion about L4. You'll notice that the zero velocity curve here is tilted by about 30 degrees off of the rotating frame. So let's make our life easier by defining a new rotating frame that matches that orientation. So we're going to place a coordinate origin at L4 and then define some new rotating directions that are approximately in the direction of this contour. And we will call this frame C, with this direction being C1 and this direction being C2. Let's make a slightly cleaner copy of this diagram. We have our original rotating frame B with the ER and E theta directions. The two primary masses M1 and M2 are always along the ER direction, with mass M1 being a distance negative mu star from the origin, which is their barycenter, and the smaller of the two masses, M2, being a distance 1 minus mu star from the origin in the positive ER direction. We've previously found that L4 is located at 1/2 minus mu star in the ER direction and √3/2 distance units in the E theta direction. And here now is our new reference frame C, with C1 always pointing 30 degrees below the ER direction. So C is rotating at the exact same rate as ER and E theta. The only distinction is that there is this constant orientation offset between C and B. And here we have our point P somewhere in space, but near L4, because that is the motion that we're currently interested in. We can write the position of the point with respect to M1 as, that is, the sum of its position with respect to the L4 point plus the position of the L4 point with respect to M1. We're going to define a new set of coordinates describing the position of our particle P with respect to L4 in the C frame. So X prime, Y prime, and Z prime will be the components measured along C1, C2, and the C3 direction, which is the same as the E3 direction that we originally had. And as before, we're basically going to be ignoring the Z component of things. So we're just going to set this to 0. By inspection, we can write the direction cosine matrix between the C and the B frames as, that is, cosine of 30 degrees, negative sine of 30 degrees, sine of 30 degrees, cosine of 30 degrees, and everything else is zeros and ones because we're rotating about the third unit direction. We now write, that is, the C frame components of the position vector of the particle with respect to mass M1 are X prime, Y prime, 0, which is already in C frame components. That's this term here, plus this direction cosine matrix multiplied by the components of this vector, R L4 rel M1, in B frame components. And these we know are 1/2 minus mu star plus mu star, because we're taking this distance, which is 1/2 minus mu star, and then subtracting this distance, which is negative mu star, hence this first term, and then we're just taking the E theta offset, which is √3/2, and the L4 point is in the ER E theta plane, so the Z component is 0. This whole term evaluates to, because as you will recall, the cosine of 30 degrees is √3/2, and the sine of 30 degrees is 1/2. And so what that means is that this entire expression boils down to the position of our particle with respect to M1 in C frame components is just our new X prime coordinate, our new Y prime coordinate plus 1 distance unit, and 0. The magnitude of this vector is the thing that we've previously called R1 in all of our equations of motion for the circular restricted three-body problem. So in terms of our new coordinates, the magnitude R1 must be the square root of X prime squared plus Y prime plus 1 quantity squared. Similarly, the quantity that we've previously called R2, which is the magnitude of Rp with respect to M2, can be shown to be equal to the square root of X prime minus √3/2 quantity squared plus Y prime plus 1/2 quantity squared. Recall now our rotating frame potential, U, which we've defined as negative 1/2 the norm of R PRLO squared minus the quantity 1 minus mu star over R1 plus mu star over R2. This whole term can now be written as, that is, negative 1/2 of X prime minus √3/2 mu star quantity squared plus Y prime plus 1 minus mu star over 2 quantity squared. We are now going to expand about the L4 point, which is x prime equal to y prime equal to 0. And we're going to assume small radial excursions from L4 and therefore drop all terms of order mu star squared and order mu star cubed and order mu star y prime. And what that will leave us with is an approximate expression for u of, that is negative 1/2 times the quantity 3 minus mu star plus 9/4 mu star x prime squared plus 3y prime squared. We are now going to define negative 2u as 3 plus gamma mu star for this new quantity gamma. And recalling that the Jacobi constant associated with L4 was given by negative 1/2 times quantity 3 plus mu star minus mu star squared. And we're going to go ahead and drop the mu star squared, just as we did in this expansion. So C4 is now being approximated by negative 1/2 times just 3 plus mu star. Plugging this into our approximate u expression yields, that is, x prime squared over 4/9 1 plus gamma plus y prime squared over mu star over 3 times 1 plus gamma is equal to 1. And this is once again the equation in Cartesian coordinates of an ellipse. The zero velocity curves about L4 are approximately ellipses based on this linearization analysis that we've just performed. And so this is now pointing us towards these closed stable structures around L4 and equivalently L5, which we can then map to tadpoles and to the more global structures that we find in the horseshoes. And there's a lot more that can be said about the particular analysis associated with this specific system, and that is covered very well in section 3.10 of Murray and Dermott, which has a lot more details.